So today we have you, Komiya, talking about gravitational and phenomenological properties of a early universe defects.
Well, that would be a typo for me, I
Sorry,
suppose. Well, thank you very much. Okay,
got
great.
me
Thank
for
you
a
for having
second.
me. Okay, fantastic. Thank you for having me. Yeah, I'll hopefully talk a little bit about this work I've been doing with my supervisor, Fumihiro Takayama at YTP. And also I hope to probably give a little more background as to some of the motivations behind all of this. So I hope it will be a bit more accessible in terms of the topic. So yeah, I'll start with talking a little bit about the particle physics behind all of this, and hopefully that will lead on fairly naturally to why all of this is interesting in the cosmological context before I move in to look at a very specific defect, or rather composite state of defects, that's called the monopole bag. And from there, if we have time, we'll look a little bit at the physical and theoretical consequences of this sort of model. So I suppose without further ado, we'll start with the beginning. So as we all probably know fairly well, inflation is this period of accelerated expansion, and with that comes from physical scales being very rapidly increased, and also temperature would be dropping very quickly during this period. And one of the consequences of this that people usually refer to is that we will have different energy scales being reached consequentially, and this causes symmetry breaking and phase transitions. And the reason this is interesting is this can produce a lot of different signals and a lot of different objects that might be relevant to us understanding this early period in history. So for example, the sorts of objects I'm thinking about are maybe vacuum bubbles that might come from a first order phase transition, or perhaps topological defects, which we'll be focusing a lot on during this talk, and these can come from symmetry breaking. So this is mostly the inflationary period. Afterwards, we expect some sort of reheating to occur in order for us to return to the right temperature for BBN to happen. And eventually, of course, we need baryogenesis that happens by some sort of mechanism. So defects specifically might have an effect on all of these processes, which is why there is a cosmological interest, but also they might leave some sort of signal, like I said, which could include gravitational waves and CMB. And I suppose we all know that at the moment there's a lot of I guess a rush to think about the sort of models and theories in time for ELISA and all of the upcoming space probes to give us some data. So another reason that maybe defects are a very interesting way to think about this is because a lot of the signals coming from the early universe might be quite hard to decipher. You have a massive bundle of maybe stochastic gravitational waves or optical effects, and also non-Gaussianities are something that people look at a lot at the moment, but this is all really difficult to decipher. But with defects, what we do hope is that it can give us fairly unique signals because they come from very specific processes. So that's something exciting that really motivates this sort of study. So the specific phenomenological background that I would like to start with is thinking about QCD and the axions that come from it. And all of this stems from perhaps one way to describe the story is to start from the strong CP problem. So we can begin by thinking about some sort of Lagrangian that maybe looks like this. We have these gluon field strengths, and we have this term that is probably usually a total derivative classically. And we also have this vacuum phase angle, which is theta. So, well, I said classically because non-perturbatively in QCD, this is a term that can't just be discarded very easily because of QCD having a non-trivial vacuum topology. And this stems from the fact that we want, first of all, the Euclidean action to be finite. And in order for that to happen, we want the gluon field strength to go to zero at spatial infinity. And because these A mu's, they become pure gauge, then this vacuum topology actually winds, and therefore it is non-trivial, and the effects that come with this are called instantons. But this is something I'll go on to later. What's important now is that we cannot discard this term. So what we find is that overall we have this physical vacuum angle that comes from a contribution from theta and also from the mass matrix for the quarks. And what this means is that we actually have some sort of very non-trivial constant here, but that's not something we can observe in experiments. In fact, experiments put a very, very strong constraint on the size of this theta angle, which can't be very easily explained using the theory. We can't see very clearly why this has to be very, very small. And this is something that we call the strong CP problem. So one way to solve it dynamically that is thought to be pretty elegant would be the Petre-Quinn mechanism. And what this does is if we introduce some complex scalar field phi, and we say that it's invariant under this U1 PQ symmetry. Now, phi is some field beyond the standard model. It doesn't necessarily couple to inflatons or anything, or, well, there are different versions of the theory where we determine whether this phi is really something that is charged with respect to the standard model. But in essence, we're introduced this field and we say that it's invariant in this way. We can write down the Lagrangian for this, and we find that there's a vacuum expectation value for this phi occurring, and this relates to a spontaneous symmetry breaking of this U1 PQ global symmetry. Now, the reason I highlight the symmetry breaking is because there are going to be a lot of different scales in this problem, so we want to keep these in mind before everything gets really confusing. So at the symmetry breaking, what happens is we produce these Goldstone bosons, which are what we call axions, and these are massless at this current scale. So some of the other numbers that are very relevant to us would be, first of all, we note that this axion is often represented in this dimensionless form, which is the theta that we saw before. And also it's related to something called the axion decay constant, which is Fa here. And this Fa can be written in this form. We'll be carrying this notation mostly throughout the rest of the presentation. And this NdW that arises here is what we call the domain wall number. And well, for our purposes, this is a nice thing to call it, but really it relates to the QCD color anomaly. So if we have this Goldstone boson A coming in, then it actually inherits a shift symmetry from these transformations that we can see here. And this means that first order terms with respect to A are, of course, not valid. So the first interaction term we have looks something like this. And because this U1PQ symmetry is anomalous under QCD, what we eventually have is that instead of the previous theta bar that, if we remember, comes from the vacuum phase angle and also from the mass matrix, it now has this extra contribution that is this A over the decay constant. And this gives us some effective theta value. And if we continue to go down the scales, we reach QCD scale where strong coupling comes in and non-perturbative effects activate. So I suppose historically this is going to be called something like QCD phase transition, but perhaps a more physically accurate terminology would be to call it the QCD crossover, which is what we'll do from now on. But anyways, at these scales, these instanton effects are no longer suppressed. So it tells us that the vacuum manifold is no longer trivial. And we generate this potential for the effective theta. A quick note on the notation here actually is that we won't be carrying forward this theta effective notation. It's a bit clunky. We can rescale everything, and from now on, we'll be using a much cleaner way to display it, which is that theta is itself this A over Fa. So let's take note of that so we're not confused later on. But anyways, after generating this potential, we see that this theta has a shift symmetry, and we also see that the electromagnetic terms look a bit more interesting. So typically this Chern-Simons FF tilde term is going to be a total derivative, so it doesn't have any physical contribution. But in this case, of course, we're introducing a variable theta, we have a dynamical theta, so this whole term is going to give us something interesting later on. So in essence, we have generated this low energy effective potential in this effective Lagrangian. So we see that now this total theta dynamically stabilizes at 0. And that is how we solve the strong CP problem via the PQ mechanism. So the PQ mechanism I should really specify is something that's very much related to a QCD context. If we wanted to step away from QCD and look at axions in a more general sense, then what we'll really be thinking about are ALP models. And this is a much wider class of models that might come from a completely different origin to QCD. It originates from string theory and from different gauge properties. And what this does is it really decouples the whole thing from the constraints of the QCD confinement scale. So this allows us a much wider range of the axion mass, which activates also at QCD scale in the QCD case, and also the decay constant. So this combination can be a much wider range of different values. And this is interesting because it relates to how this theory and this model interacts with the cosmic timescale. And this changes a lot of things about the evolution history and formations of defects that might have arisen. So let's move on to exactly that now, where we think about maybe how this theory integrates into cosmology. So if we start with some model that is happening post-inflation, then first we find that at some temperature that is related to this decay constant or the symmetry breaking scale, this U1PQ symmetry will be spontaneously broken. And what happens at this point is that we actually generate axion strings as topological defects. So the reason for this is that if we think about some sort of top hat potential, then of course the vacuum manifold is this degenerate S1. And if we wanted to continuously deform this manifold to some central point, then we can't really do that because we have every phase coinciding at the center. So the solution for that is that this is an axion string where this phi is going to be 0 in the center. So we have a winding of theta going around 2 pi around the string. So this is the first thing that occurs, and if we remember the scales that we highlighted, this is at PQ symmetry breaking. And the next thing that happens if we continue to decrease temperature is that we arrive at this TQCD, and at this point, the PQ symmetry is explicitly broken into Z NDW, which is the domain wall number from before. And we can see that because we know that this is where all the non-perturbative effects activate and we generate this effective potential. And at this potential, we see that this theta now has degenerate minima. And what this corresponds to physically is that we form domain walls that surround this axion string that we formed before as having this axion string as a boundary. And we can see that by looking at a very simple case, which is where domain wall number is perhaps 4. And we see that, of course, theta needs to wind by 2 pi, and these walls separate regions where we have theta being 2 pi over NdW times by some integer n. And of course, 0 and 2 pi are the same region that are degenerate. So we can see this as a very physical picture. So this network that forms this network of defects is like a string wall network. It's massive. It's infinite. But along with that, we also generate possibly closed loops. So closed string loops are possible, and also closed spherical domain walls are also possible. And as a whole, this whole network is oscillating and emitting axions, possibly perturbing the gravitational wave background. And also these closed loops are dynamical in their own sense. So closed loops are particularly interesting for us because they're a lot easier to model analytically, instead of perhaps having to model the entire network as some elastic matter or some elastic fluid. We can think about these closed loops as mostly spherically symmetric, and the overall dynamic evolution of them is that they will collapse. So overall, we see that we have various particles being emitted, and if we have some sort of collapse, we might expect relics coming from this whole scenario. And the sort of things that are generated by this is very much related to where we place everything with respect to inflation. So if we suppose PQ symmetry is broken before inflation, then the only constraint on this is isocurvature perturbations, which is a very well-known constraint on axions and also on the inflationary Hubble scale. So in this scenario, we have these axion strings being formed before inflation, and of course during inflation, they're very much diluted, and there's not much that happens in a physical or phenomenologically interesting sense. A much more commonly studied case would be if everything forms post-inflation. So suppose PQ symmetry is broken post-inflation, and then we have these domain walls also forming post-inflation as with string boundaries. Then what we could have in the case of the domain wall number being greater than 1 is a domain wall problem. And the reason for this is because the overall network is stable in the case where NdW is greater than 1. And this entire network remains stable and eventually could overdominate the energy content of the universe, and that deviates from the cosmological standard model that we observe. And the solution for these kind of scenarios would be to introduce some sort of bias potential. And what this does is it breaks the degeneracy between the regions that are separated by the domain wall. So eventually there's this small pressure that acts in one direction or another and causes the entire network to eventually annihilate at some point. So of course, a very natural alternative is to make the domain wall number 1. And in this case, the domain wall problem is trivially solved because the entire network is unstable. So if we go back to the picture we drew before where we had a string as a domain wall boundary, then domain wall number being 1 just means that the domain wall is essentially some sort of branch cut between the 0 and 2 pi winding. And therefore, there's no topological catastrophe if we remove this. So as it contracts, it just annihilates naturally. And this can be dynamically satisfied if we impose something like the Lazaridis-Jaffe mechanism, which tells us dynamically how we might achieve domain wall number being 1. So this post-inflationary defect generation scenario is the most common case for QCD axion models, and that's purely by virtue of the observational constraints we place on the decay constant, which, if you recall, relates to when this PQ symmetry is broken. So one more case would, of course, be if everything happens during inflation. And in this case, we probably need to involve ALP models because this is the sort of alternative FA and MA that is required for this to actually occur physically. And what happens is if we form these defects during inflation, then of course they are blown way out of the horizon during inflation. And there they are effectively frozen. They move co-movingly with the Hubble flow in the background. And at some point after inflation has finished, of course, this horizon will expand and they will come back in. And once they regain this causality, their uniform motion is a monotonic collapse. And when I'm talking about this, I'm specifically maybe thinking about a closed scenario, which is a lot easier to model, as I said, and a lot more intuitive to think about. So if you think about a closed domain wall that is more or less spherically symmetrical, it will re-enter and start collapsing under its own tension in a standard case. So this is interesting because it allows us to form much larger defects, and this could have much more diverse consequences in terms of the sort of objects that might form as remnants. So remnants, speaking of which, there are plenty of different ways to talk about how they might form and what might form, but I think the most interesting one to think about would probably be primordial black holes, something that's talked about a lot as a dark matter candidate in addition to the axion, and also as something that might generate signals like gravitational wave backgrounds or lensing effects, and that's all very interesting observationally, so I'll focus on that, and specifically I'll focus on how they might arise from closed wall collapse. So as I said, the overall dynamics would be a monotonic collapse under its tension. And there are actually two scenarios, in essence, limiting cases for whether black holes can form. So the standard relation that people would quote at this point is to say that dissipation becomes most efficient when the thickness of the wall is of a scale as its radius. So when this radius is the same size of as the thickness, then of course it's dissipating very, very efficiently, and the Schwarzschild radius of the object is shrinking very rapidly. So if we have a scenario where the Schwarzschild radius is much smaller than the thickness, then this wall will effectively oscillate in the manner shown here. And I don't think I cite it here, but this is from a very seminal paper by Woodrow where he simulates the process for the first time, and essentially the wall will eventually dissipate. And in the opposite scenario, what we have is essentially that the Schwarzschild radius of the object stays sufficiently constant throughout its collapse, such that we can reach a stage where the radius of the closed wall eventually comes within its Schwarzschild radius, and we have catastrophic collapse, forming a primordial black hole. So there are lots of other different ways to achieve this if we have some sort of roughly spherical overdensity region, or if you have a closed loop of cosmic string, for example. And these are, of course, also very interesting to study, and also very important is to think about the emissions that come from these black holes once they form. But for the time being, this is the most interesting process that I think I should cover before moving on. So now that I've given you maybe some background about the sorts of defects that might be relevant to an axionic scenario, I'd like to introduce this very specific case, which is a composite defect formed from an axion domain wall and a magnetic monopole. So to get some intuition for these monopoles, they come from some sort of symmetry breaking, for example, through Young-Mills in the gut scenario. And the classical case for this would be a 't Hooft-Polyakov monopole. And we can think about introducing some Lagrangian that looks like this, where phi is the Higgs and everything is in a triplet representation. So in this case, some symmetry breaking will occur, and we form this monopole, which is essentially some core inside of which we're obeying the original symmetry, so SU2 perhaps, and outside we're tending to some asymptotic region with U1 symmetry, and all the gauge fields become abelian. And this core region defines the central area of the monopole, or rather really the size of the monopole, and the scales as something like 1 over the mass of the monopole, where alpha here is also required, that's the fine structure constant. So one schematic way to think about this monopole object in a more geometrical sense is if we, of course, we need the exterior region to be asymptotically flat. We can think of this core as roughly some sort of domain wall with a very small thickness, and the interior region is going to be more or less modeled by de Sitter, and it's going to be also non-singular at the center. And what this does is that we allow the outside and the inside to be matched physically, and the reason for this is they will have to obey the Israel-Dalmor conditions, which tells us that the induced metric is continuous across it, and it also tells us something about the intrinsic energy stress tensor of the domain wall that forms the boundary. But for this case, currently we're staying in flat space, so this is just something to keep in mind later. And also something to keep in mind is that we won't specifically be taking a 't Hooft-Polyakov monopole in a lot of cases, but this is just a nice way to introduce how everything works. So a bit of terminology is that if these monopoles, they acquire electrical excitations, there will also be a mass transmutation, but the final states with both magnetic and electric quantum numbers are called dyons. And the reason I introduced this is because these can form in a very interesting way if we place these monopoles in an axionic background. And this effect is called the Witten effect. So if we take some version of the Lagrangian we had before and we add on these axionic electromagnetic terms that we are now familiar with, then what we have is that there is an effective extra conserved current, which is the Witten current, modifying the equations, acting as a sort of source term. And what we have effectively is this extra electric charge upon the monopole. And if we think about everything in terms of the allowed charges, we can define this minimum magnetic charge allowed by quantum mechanics, and we find after some mathematics that the charge induced on this monopole by placing it in a non-zero theta vacuum or axionic background is something that goes as this. So from now on, we'll be taking G equals to 1. This is just a choice that gives us very physical and simple solutions. We can also change this and things will become a bit more complicated, but this is taken without loss of generality. So in summary, the Witten effect is saying that if we place a monopole within a variable theta background, then we will form these dionic states instead when theta is not equal to 0. And one more point that I should probably cover is that monopoles are, of course, in this case, the definition of an object that does not have electric charge. So if we take n equals to 0, then essentially we're starting with a monopole state, and we can add theta non-zero, and then we'll start moving up into dionic scenarios.
Sorry,
So
sorry to stop you. What's G?
G is basically E, I guess, for the magnetic analogy, if that's the easiest way to think about it.
Can you, if you don't mind, can you go one slide back just very
Yeah,
quick? I see. Thank you. Sorry.
no worries. Thank you. Okay, so I mentioned some standard theta vacuum that might be non-zero, and I mentioned putting a monopole in it. And the monopole bag is essentially a very specific case that it's a term coined by Kogan as he constructed this object for the first time. And it's essentially if we specifically have an axionic domain wall and we place a monopole within it. So we're still having exactly the setting that we were describing before, where there's a non-zero theta background and we're placing a monopole. So let's start with a very specific case. We can, as a side note, we can change all of these boundary conditions and things will still be physical as long as we choose them sensibly. But for the sake of argument, from now on, we'll take the case where we have a domain wall, and this domain wall is interpolating between an interior region where theta is 2 pi and an exterior region where theta goes to 0. So in this case, we place a monopole in the center and it becomes a dion, because like I said before, we'll take n is equal to 0 for this simple illustrative case. And then the charge on this monopole is now going to be E times theta over 2 pi. Theta being 2 pi, the charge is E. So we have a dionic state in the center, and by that logic, we can define these radial fields coming out from the state. So there will be magnetic as well as electric fields, which are defined as shown here. So a couple interesting things to note. The first is in this scenario, we have an effective overall dion state that is this wall plus the central dion because of the quantum numbers of the scenario. And however, this interior electric fields are entirely shielded in an ideal scenario. And this is because we're taking theta to be 2 pi in this very small region, small r region, and therefore this effective radioelectric field will be 0 within the domain wall. And a second thing to note is that, of course, we can define some total energy of the system coming from the EM terms, which will go as E squared. So what we find is that if we have this interior theta deviating very much from 2 pi, then as we go to very small r, this energy is going to start blowing up. So what we have is an effective repulsion acting on the wall. That is to say, we're keeping the wall at some distance, we're maintaining theta equals 2 pi at some distance determined by the strength of all the interactions. And that is to prevent everything from becoming very unphysical and going to infinities. So what Kogan also says is that if we form this object, we can actually find that the domain wall goes to some radius at which it is stabilized. So a very simple way to see this would be to write down this effective Lagrangian encompassing all of the theta relevant terms. And we can write down an equation of motion for this. By defining some sort of effective potential and minimalizing it, we determine that this radius at which everything becomes balanced, which is to say the balance of the domain wall's contraction by its own tension and the balance from the electromagnetic terms, which are forcing this theta to stay at 2 pi for a certain distance before everything blows up, is this RB, which is a bag radius. and it goes as something like 1 over Fa, which is the accidental K constant from before. So this composite state is of interest because usually, classically, bare dionic states are not said to be stationary. So in this case, we're having an effective state that is stable and, well, I suppose acts as a mini dion, but comes from a composite scenario and is entirely stable in its construction. But of course, we're defining everything in flat space at the moment, and the very natural extension would be to think about this in the gravitating context. So we can go back to our previous picture for a monopole core, where we say that the interior looks something like a de Sitter. It matches to some asymptotically flat exterior, which is some sort of domain walls at its core radius. And by the way, this diagram is very much not to scale, of course. And then we wrap an axionic domain wall around it as well, which is closed. And so we're essentially forming exactly the monopole bag state, but we're defining the core to be shown as such, and we're defining the entire exterior to be asymptotically flat, as we know from Buckov theorem is necessary. So yeah, we're maintaining exactly the same boundary conditions as before, where at very small r, we want theta to recover 2 pi by the Witten quantization condition. And at very large r, we want everything to decay to 0. And of course, like I said before, we can shift these boundary conditions around within the realm of feasibility, and everything is still physical. And we expect this point at which the domain wall drops and causes the theta to plateau out to be defined around the our bag radius. But of course, we want to solve for that dynamically. And to do that, we define first some GR ansatz. And the way we define this is there's going to be some metric function C, and this GRR term is actually not going to be just C, it's going to be also multiplied by some function n, and this n will have certain boundary conditions upon it that we'll discuss in a second. But the purpose for this is if we go through and solve all the equations of motion, then we find that this n is in fact very much necessary. So if this n was just to be 1 and we have a very standard Schwarzschild ansatz, then we have A prime going to 0. And of course, this is a very valid solution, but it's a solution in which the scalar field is going to basically be flat. So in this non-vacuum setup, we have an ansatz that looks like this, and we can write down all of the standard equations of motion as shown here. And in a GR setup, of course, we also require the Einstein equations, which are shown here. So I've manipulated everything a lot. Please don't worry about this. There are lots of different ways to go about this. But the essence of the problem is we want to narrow it down so that we have a couple variables and we numerically solve for everything within the realm of these boundary conditions here, which are more important. So this is everything we covered before. One thing that I should note is that, of course, we're using some A instead of the dimensionless theta now. And this A, of course, goes to 2 pi Fa in the very center core region, and it goes to 0 asymptotically. C is the metric function. We can ask it to go to some sort of constant at the core, where we remember we need these matching conditions for everything to be continuous geometrically and physical. So we're going to choose that to be 1. And we also want it to be asymptotically flat. So A goes to 1 at spatial infinity as well. And this n that I've discussed before, we can see now that it acts as some sort of redshift, I suppose. And we want it to go to some constant at the core as well. And we want it to go to 1 so that everything recovers a Schwarzschild, or in this case, because of charge, Weisen-Nordstrom solution at asymptotic distances. So also there's this energy momentum tensor that we can write down. And in future plots, we will plot actually the energy density. And the reason for this is because this energy density depends very much on these terms here, which in future we will see I'll refer to as rho fields, because they are related to the behavior of this axion profile. And these will be the parts that relate to the electromagnetic components of the theory. So if we go ahead and ask our favorite code to solve this, then we get something that looks like this. So a couple things to note. I impose the cutoff at some small r in order to avoid the infinities, and this cutoff is defined somewhere around our core. And then plot everything. So we plot the metric functions, which are C and N, red and blue. And we also plot the axion profile A, but one thing to note is that it's on a separate y-axis so that everything looks nice and is readable. And then we go ahead and plot the total mass, which is just integrating over the energy density. And like I said before, we split the energy density into total contribution, which is all of this, and also rho fields, which are only coming from the axion-related terms. So here we're plotting everything under a very standard QCD axion parameter space. And what we see is that we recover something that looks very solitonic. So this metric function, it doesn't cross 0 at any point. everything is very similar to flat space case. Mass becomes asymptotically flat, so that's great. Nothing is exploding, and everything looks very, very tame. So if we actually shift everything now into ALP parameter space, so that means our axion mass is going to go down, go up, and the decay constant is also going up. And what that effectively tells us is that the domain wall is becoming a lot more massive. Then we see that everything becomes a bit more interesting. So in this plot, I'm overlaying the flat space solution that is predicted by Kogan's analysis. And we're also plotting the curve space solutions, which are the solid lines. And yeah, we can see a couple different things here. So first of all, this metric function C is now seen to dip below 0. It changes sign, and we can fairly reasonably interpret this as horizons forming, and we probably have some sort of black hole-like solution here. One more thing is that this A, the axion profile, is moving inwards compared to the standard solution that hits somewhere around 1 over FA. And this N is now no longer just a flat line. And if we think about what I said before, where I said that this N has to be a dynamical function, because otherwise it means that A has to be flat. Of course, N is flat here, but A is not flat. And the reason for this is that this, in the equation for N, it actually scales something like 1 over M blank. So when N is way, 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 way smaller than M blank, it barely moves, but that's not because A is flat. And in this case, of course, everything is becoming way heavier. So this N does perform exactly like we might expect it to. It goes to 1 at spatial infinity, and it recovers some constant that is fairly small at the core. And this is, like I said before, some sort of redshift. And much more interesting is if we look at these, the masses of everything. So the total mass looks fairly similar, but we see that if we compare the curved space and the flat space energy density coming from purely the axion components, then we see a couple interesting things. So this curved space axion parts actively now contribute to the total energy density of the system, which is very natural because of course we have very much heavier domain walls. I can see that by this little bump here. And also we see that instead of coming down very sharply and recovering a flat axion profile that is A prime equals to 0, that is rho is going to 0. It maintains some sort of non-zero axion profile at very small r. And the reason for this is where then essentially in the beginning where we had a flat space scenario, the two forces that are balancing are the intrinsic domain wall tension that is contracting and the electromagnetic term that, as I said before, is forcing the entire configuration to maintain theta equals 2 pi in the center. But as we crank up the mass of the domain wall is collapsing and it's coming into a region where its own gravitational force is actually relevant. So it's trying to contract, but more strongly than before in the flat case. However, the electromagnetic terms are still forcing everything to stay very much close to theta equals 2 pi in the very core region. So what essentially happens is that in the core, the gravity is causing everything to roll as much as it can towards theta going to 0, while EM is forcing everything to stay at theta equals to 2 pi as much as possible. So instead of this very sharp and very clear profile we had before, where A prime is basically 0, sharply we drop, and then A prime recovers 0, we have actually a region here that is some A prime non-zero rolling very slowly towards A equals to 0. And we can see this a lot more closely, clearly if we plot directly the profile. So we're plotting the gradient of this axion profile now, and we see exactly what I just described. So in the flat case, it's a very, very clean profile, but in the gravitating case, we have this deformation in the shape. Yeah, this is just something to demonstrate exactly what I said, but a bit more clearly. So in this case, we're changing the charge by adding this multiplier. So as charge gets cranked up, we see that we go into this scenario where A prime starts lifting way earlier in the center, and that's just because electromagnetic terms are a lot stronger, and that they're enforcing this theta equals to 2 pi very strongly in the core, and that's why we see that it's pushing the radius of the domain wall further and further out as we crank up the charge. And in the exactly opposite scenario, where we increase the decay constant, we're increasing the mass of the domain wall, so it's collapsing everything as much as it can. And once the mass gets large enough, we see that there is, in fact, this lifting, just as before, due to the two forces fighting it out in the center. So the reason any of this is interesting, so I hopefully will think about defects in general, as well as this particular composite state, is that, well, primordial black holes. So I mentioned before that they can be formed from these closed domain wall collapse. And there are a couple of things that have a great effect on whether they do form primordial black holes and the amount of primordial black holes they form. And one of the things is something that I mentioned very briefly already, which is that there are certain parameter spaces where the mass of the black hole is not sufficient. That is to say, the mass of the black hole is only sufficient to start dissipating at some point. And sorry, the mass of the domain wall is only sufficient to start dissipating rather than actually reach catastrophic collapse. And the condition I gave you prior to this was that the thickness and the radius must be related in some way. So if we consider this scenario where we have some stabilizing boundary condition on each side, then there are a couple of things we could I suppose speculate, as we haven't done the particular analysis in detail at this stage. So perhaps we can imagine a scenario where the mass is not originally expected to be sufficient to form a primordial black hole. But because there is this boundary condition in the center that is anchoring theta at 2 pi f, maybe we can imagine that these masses where usually you will have dissipation occurring very quickly and the wall will eventually disappear into nothingness, we have something that keeps its shape for a much longer time. And eventually maybe we will observe something like this sort of collapse where we have horizons forming and a primordial black hole taking the place of something that would otherwise just be a bunch of axion emission. So that's one thing that really affects the formation of remnants. And another thing is that the projection of how many primordial black holes can form from a particular scenario also relates on also rests on a lot of assumptions. So in the case of these closed walls or closed string loop collapse, then oftentimes we need to assume some level of sphericity. That is to say, spherical symmetry is maintained, and under this assumption, we calculate the abundance of primordial black holes. So any deviation from the spherically symmetric scenario, perhaps an elliptical case, would definitely impact the number formed. And another thing that impacts this in a very similar way would be angular momentum, which is usually assumed to be zero. So in our gravitating monopole bag analysis, we did observe that the shape gets deformed if we think about it in a much more physical scenario than a flat solitonic background. And in this deformation, what we have is essentially a much thicker wall than you would otherwise expect. And this has a couple of different consequences. So if you have a thick wall, then you might not be able to apply the thin wall approximation on it, of course. And in this thin wall approximation, we're assuming that this is an infinitesimal surface. There are no fluid dynamics or anything happening within it. But in the thick wall scenario, then there would be. You might expect some shear and frictional components. You might expect perturbations that are in the background in the cosmic medium to be transferred onto the wall in some sense. And as a consequence, you might expect there to be some sort of dynamic motion, and be that deformations that cause a deviation from spherical symmetry or some sort of global sense of rotation or movement. This would all have an impact on the formation of primordial black holes. Specifically in the case of rotation as well, you might expect this to have some sort of gravitational or optical imprint. And the reason for this is you might expect there to be some multipole moments. So instead of a perfectly spherical object, you have one that might emit gravitational waves. And furthermore, if you have some rotation going on, then you would have some lensing effect affecting the background that we view through these primordial black holes. And that's something that's been actively looked at in the case of primordial black holes. But if we consider maybe a domain wall or some sort of monopole bag doing exactly the same thing, then we might also have effects coming from that as well. And one more thing is that this type of object actually has a lot of theoretical relevance. So one very obvious thing to think about is the no-hair conjecture. So in this case, we definitely have some sort of scalar field, and it's non-trivial. But of course, the no-hair conjecture in particular, the Hui-Nicholas version of this, tells us that we expect any scalar field in this scenario to go to zero. But we're evading this particular conjecture in this case, where we have this theta ff tilde being some sort of source term. So we're exactly evading the assumptions that they have put on. And this is a very similar scenario to the Lee-Weinberg charged black hole scalar hair scenario, which is very similar. They propose some object with almost axionic scalar hair, and they numerically solve for the profile that might come out of this. So the difference being, of course, that they have no axionic profile. They're simply, no axionic potential. They're simply solving for a free scalar. And it's what you can think about the monopole bag as is a specific case of this where we have a particular construction. On the topic of this particular construction, The central monopole region is one way that we evade something called the Broodnikov condition, which is to state that if we have some sort of regular black hole construction with maybe ionic charge on it, then we cannot have electric charge in particular. So a lot of constructions only look at magnetically charged regular objects. But a very typical way to evade this is in the sense that we can add some sort of core matching conditions, and we define the core region to have a particular structure, and this is a very neat way to evade the Broodnikov condition. But at this point, I should, of course, specify that our analysis is perhaps a much more simplified version of a more detailed and analytically complete description of this object. So you cannot conclude from what we have so far that we definitely can form a regular ionic object, but I think it's a very nice indication for perhaps a construction that doesn't require modified gravity or any really exotic electromagnetic interactions. It simply uses ingredients that we're fairly familiar with, so axionic theories and monopoles, and simply applying gravitational theory to it, which could be something that is very nice. And one last thing I'll think about is when I mentioned before, if we have primordial black holes, maybe we expect them to be emitting through Hawking radiation. And if we have these string wall networks, we expect them to decay and emit axionic radiation. And of course, thinking about specifically our case of this composite monopole bag defect, then we can also maybe predict what might happen in this scenario. And a couple interesting things that come from predicting this is, of course, thinking about whether stability is actually guaranteed. And if we recall one of the plots that we showed, we might have some horizons arising in this scenario. And in fact, we have two horizons. And this invokes something that people call the Cauchy instability, which tells us that having a Cauchy horizon, which is the inner horizon in Reisner-Nordstrom black holes typically, means that there is going to be some sort of mass inflation instability at the horizon. And the reason for this is if we imagine an observer sat on the horizon and everything becomes time evolving, and we imagine there's radiation incoming towards the Cauchy horizon, then what this observer actually sees is this infinite blue shifted sheet of radiation, and that renders the interior of the Cauchy horizon unphysical by something very similar to the cosmic censorship conjecture. And by this argument, a lot of people who construct Reisner-Nordstrom and also Kerr-Newman black holes do mention that the object needs to somehow evade this issue with the mass inflation at the Cauchy horizon. And relatedly, people who construct regular black holes with more than one horizon have thoughts about this being a similar issue. And while I can't actually supply a very nice way to evade this at the moment, because I don't think there is a universally agreed answer at the moment, what is interesting is that people do propose if we have an extremal final state, so if we have these horizons merging throughout its evolution and forming an extremal black hole, then we are very dynamically and very naturally evading all of these issues. And taking the particular example of this monopole bag case, what we have is a central region that determines the charge of the object by a mechanism that is not relevant to the fluid properties or anything like that. So if we have this object and we have horizons, then we can expect Hawking radiation, but we don't expect the charge to be changing. So there is a very natural way to evolve towards extremality in this particular scenario. And one more thing I will talk about at this point is that regular black hole construction in itself is a very interesting topic. Of course, if we think about everything quantumly in a string scenario, then there's not really much interest because we expect everything to become non-singular in some way or another anyways. But in a gravitational sense, it's very interesting to try and construct these regular objects. Sometimes we require, as I mentioned just now, some different gravity theory, maybe higher order interactions. And similarly, we can also access regularity by some exotic property of the fluid that is what the actual black hole is composed of. And one way to do that is perhaps with nonlinear electrodynamics and higher order interactions in the electromagnetic sense. And in these scenarios, there is this element that needs to be taken care of, which is possible instabilities to perturbation. And this is a very much more detailed study than something that we have undertaken at this point. But if we can propose a construction like ours and we can justify it, then it actually takes care of these instabilities in a very clean way. I'm not going to go into that at the moment. I think I'm coming up to a very good time to conclude, so I'll conclude in a fairly leisurely manner. So what I've hopefully described today is that we start with some phenomenological background. We start with some motivation for considering axions and related theories, so axion-like particles, for example. And I've hopefully shown you that these have very phenomenologically rich consequences in cosmology. And specifically, this comes from the fact that in an axion theory, we have a sequence of symmetry breaking occurring at different energy scales that happen somewhere around the inflationary period, where if we change the parameters of the model, we have very different dynamics. And in these different dynamics, we also find that we get very different emissions and very different final states. And then I gave this example, which is a composite defect that was proposed by Gauguin and termed a monopole bag, where we have specifically an axionic domain wall surrounding a magnetic monopole. And I hopefully showed that in the gravitating scenario, differently to the flat case scenario, which is already analyzed, we might expect this profile to be a lot more extended, and we might expect this object to form some sort of black hole-like solution. And this is something that has very close ties to related areas of study. So one example are these compact black hole mimicker objects, for example, gravastars and also magnetars or magnetars, I think is something as well. But you can have these compact objects that have fluid properties, and you can think about them as like a shelled structure, which is very similar to this composite monopole bag case that we've thought about today. And of course, we can also relate these shell-like objects to things like vacuum bubbles in fast-order phase transitions that I mentioned before. And maybe some of the dynamics will be very applicable in the sense that if we have a thick wall or if we have a strongly gravitating scenario, we might expect some difference in the dynamics. And with respect to things that I would like to think about and something that you could do with this going forwards, I did mention very briefly nonlinear electrodynamics, and the reason for this is because you could possibly generate a much more general case by thinking about this nonlinear coupling, and we might have some general fluid that doesn't necessarily rely on any matching conditions in the core or any interaction between specific objects. And you might be able to construct something similar in this scenario if we specifically think about an axionic Chern-Simons coupling and some extensions of that. So for example, axion dilaton Born-Infield. So that might be something very interesting to think about. And very related to that is to think about the UV effects. And this would relate to constructing a more realistic core model rather than dealing with it as a sort of cutoff and imposing that it has a certain geometry within. And this would also relate to as we approach something very close to Planck scale, then you might expect there definitely to be corrections. And a full consideration of all of these corrections would help with things like determining stability and thinking about evolution in a dynamical sense. So yeah, I think that's all I have to say, and thank you very much.
Great, thank you. That was a very, very nice talk. Thanks.
Thank you.
I guess if people have questions.
Okay, maybe I can ask one thing.
Yeah.
So I understand that in some of the cases, this axionic solution has hair, right?
Mm-hmm. Mm-hmm.
Is that something generic or is it somehow fine-tuned?
It is generic, I believe.
Okay, then
So
let me ask a different question. Have you checked whether this is stable, this hair?
whether the hair is stable, no. So the stability of the object at this point is coming from the minimalization of total energy, which I have checked, and also from the actual interactions and the conditions coming from that. So specifically the boundary conditions imposed by the Witten effect. So in that sense, I can say I think it is stable. But in terms of genuine perturbative analysis and thinking about maybe quantum effects as well, then no, I have not.
I see. Okay, thank you.
Great, thank you.
But I imagine without the Chern-Simons coupling, there is no hair, of course, right?
No, there is not, yes.
Okay.
Maybe could you go back to slide 11?
Yeah.
Yeah, so this picture on the bottom right, I was a bit confused about what it's saying. What's the orange and the blue here like
So
mean?
the orange is the horizon during inflation, which stays more constant. And the physical scale, so for example, the radius of the wall is going to keep increasing very rapidly during inflation. So eventually exits. And once it does, it's frozen in some sense where it becomes co-moving. And after inflation, which is this side here, um, the the objects re-enter the horizon. And once they do, all of the parts of the objects, they become causally connected again, and therefore there can be a collective motion, and that collective motion has been determined to be a monotonic collapse.
Okay, thank you.
Thank you.
And maybe could you go a few slides forwards? I
Yeah.
think to a bit more. Okay, maybe back, sorry. I think closer to maybe 14.
14.
No, 16. 16.
Yeah.
So in the far field, are you saying there's no electric field and only magnetic, or
Uh, yeah. So in the far field, no, in the far field, the object behaves like an overall dionic state. So in the
okay,
far field,
okay,
we go to zero, and we have a very standard set of equations. But in the small field, so within this domain wall region where theta is still 2 pi, give or take, then there should be no electric field.
okay, so it's just magnetic inside.
Yes.
Okay, okay,
So the
interesting.
electric charge coming specifically from the dion in center is
Hmm.
perfectly screened by the axion domain wall.
Okay, thank you.
Thank you.
Can I just follow up? I wanted to ask about this fine-tuning of this hair. Maybe it's a silly question to ask, but it
Mhm.
seems to me like you have to somehow tune this little a function to get the hair. Am I wrong, or is
Tune
this
crystal A function. I
you
don't,
you had this little a of r at some
yeah.
point, right?
I assume you mean this profile has to be tuned. Is that your question?
Yeah. Or is
Um,
this
no. So this shape is general to domain walls. So if we think about a theory that perhaps is a lot simpler, so if we go to uh let's see. So yeah, suppose we have a Lagrangian that looks like this and we forget about the this gluon field strength term,
sure,
then we
sure.
have something that looks like this, and we can say that this phi forms a domain wall once symmetry breaks.
Okay.
And in this case, we can solve a sine-Gordon equation, and the shape of the domain wall that comes out of that is something that looks like an arctangent, I believe. And
Mm,
when you do that, when you plot that, it looks exactly like this. So this shape of the domain wall itself is completely general to the to all theories that form domain wall, more or less. Of course, it's modified in this case by certain interactions, but that modifies more the location than the overall behavior, where it by definition does interpolate between these two vacuum regions. But I suppose maybe it is confusing that I'm saying I'm picking these specific values at the center and at infinity, but that I suppose is a consequence of this shift symmetry inherent to the axion theory. So I can pick this to be 0 and that to be 2 pi, or I can pick this to be 2 pi and that to be 4 pi. And the physics itself would not change. It would change the shape of the curves on the graph, but the physics should be um, the physics should be general.
I see. Okay. And this theta r is of course some redefinition of this AR that I was talking about, yes?
Exactly.
Okay. Thank you.
Thank you.